Well, hey, it's Dr. J. I am back with another lecture on limits at infinity. This will be the third part of this series and the conclusion of the limits at infinity. So we have just one main topic to resolve, exponential functions. And we're going to define a limit that previously in previous sections did not exist. So recall that if I said the limit as x approaches infinity of e to the x, previously we would say that this type of limit did not exist. Right? Remember that? And it might not have been this function. I know that we defined e in a previous video as approximately 2.718281 . It's an infinite, non-repeating, non-terminating, irrational real number. And so when you take this number and you raise it to a very large power, there is no real number L such that the limit equals L, right? You remember that? And so anytime that the limit did not exist, it meant that there was no real number that it actually equaled, right? And so there was lots of different possibilities. There was, sometimes it would equal 5, and then on the other side it would equal 2, and if those two things didn't equal the same number, we would say the limit doesn't exist. Or when we talked about polynomials and rational functions, and today exponential functions, when you plug in a very large number for x, which I'm going to do in a minute, although I don't even think I have to plug in a very large number. You plug in a number, it blows up and gets very large, and it does not approach a particular number. Well, this causes some problems moving forward. One problem is, on my end, it gives too many answers of DNE, right? And so all throughout the previous homework, there was a sprinkling, a very small number of problems where you would answer DNE, and that was acceptable. But moving forward, I don't want to give you, 10 questions where the answer to all 10 of them are DNE. It wouldn't be very helpful. It wouldn't be very useful for your, mathematical development to just be typing DNE for all these answers. So we would like it to exist, right? As mathematicians, we would like to have some way of saying the limit exists. And in mathematics, it's very easy. It's one of the beautiful things about this subject. If you want something to exist that doesn't exist, all you need to do is make a definition. That's it. Then it will exist. When you think about that, it's a real deep philosophy. Everything in mathematics was created by us, by human beings, by our definitions. And so when we define what E is, right? Then it became into existence. We defined this symbol, infinity, and it came into existence. In fact, we defined all the numbers. Right? They don't exist without us defining what they are. So let's just do exactly that. Definition, and then it will exist, and then we'll be able to put something here instead of DNE. Right? So we're going to define it to be a symbol. The limit as x approaches infinity of f of x is equal to infinity if, so these are the conditions for the limit to exist, for every value greater than 0, we'll call it M, there exists, I should say, an n greater than 0, another value greater than 0, such that f of x is greater than m whenever x is greater than n. And that will be our definition of a limit equaling infinity. And notice we are now using the equal sign. We're saying that it actually equals infinity. We could debate this for hours. Does it actually touch infinity? No. But we are defining it as a limit to be equal to infinity. It doesn't mean, if you take away the word limit, then this is definitely not true, right? So nothing can actually equal infinity all by itself. You know, a number cannot be infinity, right? So f of x can't be infinity. But with a limit now, as a definition, you could say the limit is infinity. All right. So let's take this as our first example. All right. The definition applies to any function, and I'm just going to have this be example 1. Just rewrite it using function notation. Find the limit as x goes to infinity of f of x. All right. So let's play around with it a little bit. Now, in some of my previous examples, in fact, going right back to the very first lecture video, I was using my old 1990s Texas Instrument calculator, which, you know, I'm very fond of this calculator. I've carried it around for years. It still works. If you lose it or break it, it's not a huge investment. You know, they're pretty cheap. The problem is I actually made a couple mistakes, which I ultimately corrected, but, you know, embarrassing to, you know, believe the number that's on your calculator and write it down as the answer, and it turns out it's off a little bit. Not much, but off by, you know, a small fractional decimal point or something. All right, so I'm getting rid of this. I have given in. And I discovered the wonders of the cell phone calculator. If you probably have all discovered this sooner than I did, because I'm old. If you turn it, you get a nice scientific calculator. It's easy to read. It films nicely on my videos. And it has all of the functions that you'll need for this course. So I'm giving in. If you don't want to go buy a calculator and you already own a cell phone, let's just use that. All right. I'll still keep my old handy one around. You know, it's way less expensive than the phone, but this is going to come in very handy. So let's see how this definition works. All right. When you think about a definition, it's really helpful to think about what these letters mean, right? M, right? Think Magnus or magnificent, yeah, or magnitude. It's a very large number, all right? So just think of a very large number. I'm going to do 20,000. You know, to me, that's a large number. Now, if you want to go higher, you can go higher because the definition says for every large number. So everybody out there that's watching this video can each think of your own large number. You can think of 1 million. You can think of 20 million, 100 million. You can even be crazy and make not even have it have zeros. Just make up some big old crazy giant number with lots of different digits. I'm on the clock here, so I want to keep this simple. So 20,000 is large enough for me. It's bigger than I would be able to graph on my graphic paper, right? So that's a very big number. It's very magnificent, large number M, right? And then N, just think any number. Yeah, and it should be a positive X value. So just think of n as an x value. So n is, I'm going to go with 10. Yeah. There exists an n. And again, this is really just a guess. I guessed several times before I got it to be 10, but what this definition says, on theorem, it's definition, says every time I pick an m, I can find, right? So you find it, any positive x value, and all you want is to verify that whenever x is bigger than that number, so x has to be bigger than 10, then e to the 10, right? That's our x. We're plugging it in, is greater than 20,000. So anytime x is bigger than 10, we're guaranteed that the function will be greater than 20,000. And then if you pick a larger number, if you pick 1,000,000, well, then n will probably be bigger than 10. Right? Probably be maybe 12. Doesn't have to be much bigger if you picked 1,000,000. I could play around with it a little bit. I don't want to spend too much on this, but I do want to show you how magnificent this is. So let's do e to the 10. And sure enough, yeah, e to the 10 is 22,026, which is definitely greater than 20,000. Now, that was not a proof, all right? This is just an example. You can call this a verification, not a proof. To prove it, you would have to be much more general. You couldn't pick a specific m. So when you pick a specific number, you're just kind of verifying that it's true. It's getting very large, right? If you want, you could try to pick a bigger number, you know, try to pick maybe, I don't know, 100,000 or something. Let's see what n would have to be for that. I'm only going to do one more. I'm basically just showing that for any number, no matter how big you pick it, I can find a number that's going to make it larger than that. I can always go bigger than anything you put out there. I don't think 10 will do it. Let's guess 12. Let's see. It doesn't have to be much bigger. Yep, sure enough, look. So e to the 12th is greater than 100,000. And sure enough, 162,754. Check. So I'm just verifying that it satisfies the definition. And I mean, I could do this all day. Yeah. Anytime x is bigger than 12, that's my n, then I'm guaranteed that this function will be greater than the magnificent number, the magnitude of 100,000. Right. I'm going to stop there, but, you know, I'll challenge you on your own if you really want to just really digest this one more time. Make this 1,000,000 and then figure out what n has to be. You know, how big do you have to go to get this function to go to past 1,000,000? Greater than 1,000,000. Not, I'll give you a hint. It's not much more than 12, right? I don't know how. I haven't done it yet, but it's you don't have to go to 20. I know that. 20 is too far. All right, well, that's it. That's the definition, and that means now we can actually say that a limit equals infinity. And so this limit is, in fact, infinity. All right. Next, let's do the other limit, sometimes known as the other infinity. That's the limit as x goes to infinite, negative infinity of f of x. Now this is how we're going to do negative infinity. We are going to change it to positive infinity and then change the x to negative x. This is the standard technique for evaluating limits at negative infinity because we have a definition for positive infinity. So we don't need to make a new definition, right? We can just say the limit is as we approach negative infinity, right? By switching it to positive infinity and then turning the x around the other direction. So this will be the limit as x goes to infinity of e to the negative x power. So I'll make a note up here. F of negative x is e to the negative x power. All right. Now, if you remember the rules of exponents or the properties or the laws of exponents, a negative power means 1 over. So e to the negative x is 1 over e to the x. So this is 1 over the limit of e to the x. Remember the property of limits? This is the quotient property. The limit of 1 is just 1. And then the limit of e is going to be infinity. And we're going to say that that approaches 0. Get my head out of the way. So 1 over a very large number. Now again, it never actually gets to infinity. Just think of a very large number. And again, by very large, it doesn't have to be, you know, a billion. I mean, you can just do 20,000. So 1 divided by 20,000. And look what I get. I get a very, very small number. If I turn my calculator this way, let's do 1 divided by 1,000,000. I already typed in the divided by, so let's just hit equals. Look at how small that is. Again, it's just going to keep, you know, if I made a table of values, it would be 0, 0, 0, 0, 0, 0, 0, 0, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And it would just keep getting closer and closer to 0. All right. We should probably remember these two things. All right, so let's make a little note up here. A little save me note. These are the shorthand. Well, actually, I don't want to write it shorthand. Change my mind. I'm going to write it all out. The full thing. Now, this is the wonderful thing about this particular section. It takes a lot of definition and things like that to get into the content, but once you have these two limits, we can just keep using these two limits over and over again, and at some point we're just going to memorize them, and this will become one of those brain clouds, but for now it's a box, and I'm saying save me for now. All right, so let's graph to kind of get an idea of what's going on. I'm just going to use 2.71 for E when I graph it. It's not necessary to be any more precise than that. All right, so here's my grid. I'm doing a scale of 2 to 1 scale. So I have a 2 blocks equals 1 unit. Just makes it a little easier to see. All right. So in order to get a graph, you're going to need, first you're going to need the asymptote. So if either of these limits is a real number, L, then there is, this is just a review, I'll say recall from the previous lecture, there is a horizontal asymptote at y equals L. All right, so which one is it? Well, they both exist now because we have definitions for both of these, but this one is the real number. 0 is a real number. So even though infinity has now been defined, it's only been defined as a limit, as a limiting symbol. We're saying it's a symbol that represents the limit. But 0 is more than just a symbol. It's a symbol that represents a real number. So that means in this case, we have the horizontal asymptote, abbreviated HA, y equals 0. All right, so when you graph this, you're going to click right here on the origin, and that's going to place the asymptote right on the axis. So that's your horizontal asymptote, y equals 0. So do that first. All right, and then you got to plot 2 points. Now, sometimes I make these multiple choice, so, I mean, you don't necessarily have to click, but we're going to be doing more of the mouse graphing as we move forward in this course and in this chapter. So I'm just showing you how to do it in this particular case so that you have it as a skill. All right. So remember, you need at least 2 points. So let's do f of 0. That's a very easy point. It's also something we should memorize. It's 1. Yeah, any constant, any non-zero constant raised to the 0 power always equals 1. So we're going to get our first point right here at 0, 1. All right, so this is the point 0, 1. Now we just need one more point, right? Remember, E is approximately 2.71. So f of 1 is e to the 1, which is approximately 2.71. That's this value here. So my second point will be 1 and 2.71. I can't do it exactly, but it's approximately 2.71. A little bit less than 3. And then that's it. Connect the dots. And there's your function. And you can actually see the 2 limits here. The dotted line is the 0. Yeah, that's the asymptote. So as you approach negative infinity, as the x approaches negative infinity, the values of the function approach 0. Yeah. And then the blue, 2.71, it's passing that point and it's going up towards infinity. So it's going to go 2.71, and then it's very quickly going to get up to 20,000 as we saw. Now, I don't really have the room to draw it here, but, you know, if I went 4, 5, 6, 7, 8, 9, 10. I'm just extending my x-axis. If my x got to 10, my x value, you already saw it in the intro, the y value would be way off the grid. It would be at 20,000. It would be like down the street or maybe, past my neighbor's house or something. I mean, if I had that big of a piece of graph paper, but I don't. That'd be a pretty big whiteboard even for me. Okay, so that's it for the introduction. That was one big long example. But now we have the results. We can capitalize on them. I'll bring the graphing board back later in this lecture. It takes a long time to be that detailed, so the rest of my graphs will be very quick, what we just call sketches. You know that. I don't have to tell you that. All right, so let's do example 2. Let's do f of x equals e to the negative x. Let's calculate both limits. I'm just going to get both parts out there right at the start. All right. Let's do, I always do positive infinity first. I haven't really been consistent about that. In previous videos, I might have done negative infinity and then positive infinity. In this video and in this homework, I usually start with positive because that's the definition that we have. So we have the limit as x goes to infinity of e to the negative x. Now this one's already negative x. All right, so I'm going to rewrite it 1 over e to the x. Well, that's equal to 0. And I'm not going to do all the calculation because I just did it. If the limit of 1 is 1, the limit of e to the x is infinity, or you could just think 20,000 or a million, right? A very large number. Then 1 divided by a very large number becomes 0. All right. Again, that's using the result of example 1 to make example 2 a lot faster. Now watch this part. This is the tricky part here. This is the limit as x goes to negative infinity of e to the negative x. All right. So notice, maybe I'll do a little scratch work here. This time f of x is defined to already have a negative. So f of negative x is e to the negative negative. That's double negative, which goes back to just e. So that means this becomes the limit as x goes to positive infinity of just e to the x. So watch that step right there. Take a screenshot if you need to. The x used to go to negative infinity, but now it goes to infinity. The negative x becomes double negative. Yeah, double negative, which goes back to being positive. And again, we already did this one. In example 1, this one goes to infinity by the definition of an infinite limit. And then a very quick graph without using the graphing board. X and Y. I would click right here on the origin. Although it turns out you can click anywhere on the axis here. So you have y equals 0 is the horizontal asymptote. So the horizontal asymptote is the x-axis, also known as y equals 0. All right, and then you click right here at 1, 0, 1. Right. Now this graph goes up to the left. You see? Because this limit, x is going to negative infinity, the graph is going up to infinity. And then this limit, as x goes to positive infinity, that's the one that goes down towards the asymptote. It's just a mirror image, also known as a reflection of the other graph. Okay. I guess if I really insisted on having another point here, it would be 2.71, and then the x would be negative 1. Right? If you really want to just be confident that it's, you know, at least 2 dots, two. There's technically infinitely many points to choose from, but I'm just choosing 2 very simple dots to plot. Okay. Well, that ought to do it for the introduction. I did 2 solid examples. We should probably save these results now. So let's save them in a cloud. I probably will have to erase them at some point, but the limit as x goes to infinity of ex is infinity. The limit as x goes to negative infinity of ex is 0. The limit as x goes to infinity of 1 over ex is 0. And the limit as x goes to negative infinity of 1 over ex is infinity. So that is what we're going to use to do every example in the remainder of the time that we have in this video. Well, let's just get right to it then. Example 3. Find the limits. Now, limit as x goes to infinity of e to the x minus 6. E to the x minus 6. Well, that would be the limit as x goes to infinity of e to the x minus the limit as x goes to infinity of 6. Yeah. The limit of the difference is the difference of the limits. We know this limit here. It's infinity. Minus, we know this limit. The limit of a constant is 6. And when you subtract 6 from infinity, you still have infinity. All right. So remember, infinity is not a number, right? Now, if this was a real number, then, you know, 1,000,000 minus 6 is not 1,000,000 anymore. But it's close to 1,000,000. It's still approximately 1,000,000. So you take something that's much larger than 1,000,000, it's infinitely large, it has no actual real number value, and you subtract 6 from it, you still have that infinitely large number. Let's go the other way. The limit as x goes to negative infinity of e to the x minus 6. That will be the limit as x goes to negative infinity of e to the x minus the limit as x goes to negative infinity of 6. All right, now I have a choice. It's really your choice. I could do the switch where I change that to infinity and then I change that to negative x, right? But I don't have to if I already know the result. So I already know the result. The limit as x goes to negative infinity of e to the x is just 0. So the switch that I did was really only to develop the result. Once I have the result, I mean, I don't have to draw it from scratch every time. So that becomes 0. And then the limit of a constant is just a constant. It doesn't matter that it's going to infinity. Right? The limit of any limit of a constant is always just equal to the constant. And so this is just equal to negative 6. And then keep in mind, if either one of these is a real number, then that is a HA, horizontal asymptote. So which one is the horizontal asymptote? It's the one that's a real number. So it's this one. So I'm just going to put a note, horizontal asymptote, y equals negative 6. All right. It's usually pretty obvious which one is the real number. Maybe later in this video, we'll see one where neither one is a real number or where both of them are real numbers. Those might be special cases, but we're still early in the lesson. So there'll be one of them that's a real number and one of them that's not. And the one that is a real number becomes your asymptote. All right, next we're going to talk about powers of exponential functions. So we call that e to the kx. E to the kx is just e to the x to the k, where k is a constant. So the limit as x goes to infinity of e to the kx is equal to the limit of e to the x to the k. And we have a property for that. I think it was property 8. You don't necessarily have to memorize the numbers in this lesson, but at one of the lessons I had you identify what property number it was, so maybe you have them memorized. If you have a limit of a function to a power, I think in the property we used n for the power, but n is still a k, and it's just a constant. I'm using k for this one. All right. So this would be infinity to the k, which would still be infinity. So it's infinity times infinity times infinity times infinity a certain number of times, some constant number of times. It's usually 2 or 3 or 4. It's, I don't know, it could be 9, but probably not much bigger than that. There's not any practical reason in this course to go any higher than that, but just think a handful, you know, some natural number power. It could be an integer. I shouldn't say natural. It could be integers or negative numbers are not natural, but I should say it's some integer power. And if I have room to squeeze it down here, the limit as x goes to negative infinity of e to the kx. Now I should mention if k is greater than 0. So it does have to be, in order for this to be true, it has to be a positive constant. And then for this one, it would be the limit as x goes to negative infinity of e to the x to the k I'm skipping a couple steps because I've already shown them, which would be 0 to the k power, which would still be 0. All right, and in both of these cases, k has to be greater than 0. If k is less than 0, I got room over here. I'll just put a little note. If k is less than 0, then these are reversed. So if the constant is a negative constant, well, then this limit will go to 0, and this limit will go to infinity. It's important that I show you it in the abstract, just using the general constant symbol k. But I want to do an actual number example. So let's go ahead and do that next. Example 4. Find the limits. The limit as x goes to infinity of e to the 3x plus 2 and then let's do the limit as x goes to negative infinity of e to the 3x plus 2. All right. So k is positive. Constant is positive. So which one are we going to do? We're going to say the limit as x goes to infinity of e to the 3x plus the limit as x goes to infinity of 2. There's your k. K is 3. It's positive, so this limit is infinity. This limit is 2. So this limit is infinity. All right. This one's going to negative infinity. So that'll be the limit as x goes to negative infinity of e to the 3x plus the limit as x goes to negative infinity of 2. Now again, if you don't have this memorized, we do because we just did it, it's 0, right? But I mean, I have a little bit of space here. I'll show you. You can do the switch. You can change the k into a negative power. But now the x is going to infinity. You don't ever have to worry about the constant. Oftentimes when you see this, you can just jump. You know that that's just going to be 2. So we often don't write that. I mean, I'm a math teacher, so I write it when it's necessary. When nobody's looking, I don't write it. I just jump right to here and say it's 2. Okay. And so now I said that if the k is negative and x is going to infinity, then it's going to go to 0. Yeah. So the actual limit comes out to be 2. And so there's a horizontal asymptote, y equals 2. Digest that for a minute. I'm not going to draw the graph. The graph would look very much like the graph that I previously drew, except for the dotted line, instead of going through the origin, or it would go through y equals 2. Yeah. But the basic shape would be the same shape. All right, how about this? F of x is e to the negative 7x plus 5. Let's find the limits. Both limits. So that one and the other one. All right, so this is going to be the limit as x goes to infinity of e to the negative 7x plus 5. And again, technically it's plus the limit of 5, but we know the limit of 5 is 5. Oftentimes you'll just ignore that 5 and work on the exponential function, and then when you're done, bring the 5 back. So again, if you have that memorized, it's going to infinity and the power is negative. Sometimes it's helpful to write it this way. I know it was for me. I'm sort of a visual learner. I understand things, by the way they look. And so when I see that, that looks like 0 to me, right? Because I got used to seeing 1 divided by a magnificently large number. That's that big M, right? I don't think of it as actually being infinity. I think of this as being like a million or a billion. It's some really big number. As soon as I see it written that way, my brain immediately goes, you are equal to 0. In fact, in a lot of my old notebooks, you'll see me just writing these big fat zeros right on top of every limit that looked like it was 0. Sometimes I put a slash through it or something. I'm just going to circle it. So you get 5. So this time the HA is 5. You could probably guess what the other one's going to be. I've been pretty predictable so far. That's probably going to stop now. But the next one's going to be infinity. We haven't seen one where one of them comes out a real number and the other one comes out a different real number. All right, so one of them comes out 5, and then the other one's going to come out to be infinity. I do have a little bit of space. I could write the math. That would be the limit as x goes to negative infinity of e to the negative 7x plus 5. I like to do the switcheroo. I like to change x into positive infinity, and then this would be double negative, so that'd be negative negative, which would turn to positive. Right? It's not a fraction. It doesn't have the 1 over. So that's just infinity plus 5, which I already said was infinity. Okay, well, I hope that's helpful. In your homework, you'll probably recognize a distinct pattern at the beginning, and then very quickly that pattern will run out. It won't be true anymore. Sometimes the limit goes to negative infinity. So the definition, the limit as x goes to infinity equaling negative infinity is defined very similar to, or similar to the other definition for positive infinity, right? It says for every magnificently small negative number. All right. It's funny that we use the word small, right? But in your mind, M should be like negative a million or something. That's what you think of. This has a very small number. I use the word small very loosely because you know, this is a business class and we're going to be talking about money very soon. It's coming. As soon as we get through all of this foundational stuff, I know I've been saying that for a while, but we started this course and it's been a couple weeks and we're going to start spending some money in our minds, the money of our minds. And if you were told that, you know, you owed, it's essentially what the negative is, $1 million, you wouldn't really think of that as a small number, right? You'd think of it as a large negative number or a large debt. But mathematically, when we say m is less than 0, we mean that it's small. That's what we mean mathematically. So negative $1 million is a small number. All right. And the rest of the definition is exactly the same. There exists an n. Now this one is greater than 0 because we're going to positive infinity. Okay. And when we go to negative infinity, if the x is going to negative infinity, we'll just do that switch of the x like we did for the other examples. Such that f of x this time has to be less than m. So farther down than negative $1 million whenever x is greater than n. So essentially on the graph, it means that x is going to the right. There's your n. But f, or the y value, is going down like this. All right. So you can think of m as being negative $1 million. Right? And then you can just think of n as being any number. It doesn't even really have to be very large. Like we saw with the exponential function, I only had to get to 12 in order for this to be, 100,000 or something. So the same thing will be true with negatives. If I want to get to negative 100,000, let's take off one of the zeros, right? Make it 100,000. We already saw the functions that we've been working with today. If you want to get below negative 100,000, that's the arrow going below it, then you only have to be larger than 12. So x just has to be anything larger than 12. Now, again, that was just one concrete example. I'm going to do many more with this new definition, parallel definition, I guess you could call it, to the other one. All right, so example 6. Time to break the pattern a little bit. Find the limit as x goes to infinity of 7 minus 6e to the negative 4x over 3e to the 5x. Now this problem takes up a lot of board space, so I'm just going to do one of them, and then I'll do the negative infinity on a clean board here. So this might take some time here. All right, the first thing you want to do is clean up the fraction part. So you're going to write that as 7 over 3e to the 5x minus 2. Yeah, 6 divided by 3 becomes 2 over e to the 9x. Ah, tricky, huh? Remember, when you divide, you subtract. So it would be e to the negative 4x minus 5x, which would be e to the negative 9x, which would be 1 over e to the 9x. Right. Now, the only reason why you don't see the 1 is because it's been replaced by a 2. So technically, this is 2 times 1 over that, but, this is calculus. You can handle a little bit of algebra. So that's just going to be a 2. All right, now we're going to distribute the limit. So we've got the limit as x goes to infinity of 7 over 3 e to the 5x minus 2 over e to the 9x Oh, I forgot to distribute the limit. The limit goes to both of them. All right, what's that limit? You have 7 divided by 3 times a very magnificently large number. That's 0. You have 2 divided by a very magnificently large number. That's another 0. So this limit is equal to 0. Now, I caution you, I'm always surprised by these. Every single time. I've done 100 of these. And they all kind of look the same. Right? I mean, you might be really clever and be able to notice a pattern. And there is one. There is a pattern. But it's not very obvious. So my first guess, I thought it was going to go to 2. Right? So I kind of have several guesses here. Right? It's just my intuition kicks in before my hand actually calculates it. Here are sort of the possibilities for this. It's either going to be 7/3, right? Or it's going to be -2. Yeah, -6 divided by 3, -2. Don't forget that negative. Or it's going to be 0. Or it's going to be infinity. Or it could be -infinity. So, I mean, there's a lot of different, multiple choices here. And I'm always surprised. When I write one of these down, sometimes I go, oh, yeah, that's definitely going to be, 7/3. And then, oh, no, came out to be 0. So here's what I recommend. I want you to do the math. This is a math course, and I don't know what you're doing on the other side of the screen here. But do the math, get an answer, but see if you have like a feeling about it. You might find out that, you're right about what you thought it was. But if you have a feeling, I wouldn't trust that feeling. Because, I mean, even the experts of calculus are wrong sometimes. Our feelings are sometimes misleading us. All right. Let's do the same problem again. I don't want to call it a new number. Let's change that to -infinity. And let's call it the second part of example 6. All right, so that's the limit as x goes to -infinity of 7 over 3 e to the 5x minus 2 over e to the 9x. All right, you can do the switcheroo. The limit as x goes to infinity of 7 over 3 e to the -5x minus 2 e to the -9x. Now, you don't have to do this. I mean, if you already know what these limits are, then that's fine. My problem with leaving them this way is I think that they're going, getting large, right? Which they are, but they're getting large in the other way. They're getting large negatively, yeah? So I like to switch it to a positive and then change the power. Again, all of these steps are just ways of understanding the magnitude of these things. If the power is negative, you can bring it to the top, make it back to positive again. And again, it's just a matter of perception. How do you perceive these things? For my way of thinking, I think much more cleanly if I'm thinking of positive numbers, right? So I switched it from negative to positive. I'm still answering this question here. but I'm using a manipulation, algebraic manipulation. All right, x is going to infinity, so this is going to infinity. Oops, this is plus, yeah. And this is also going to infinity. Oh, this is interesting. This is very interesting. Can't be resolved. So we have just discovered the next unresolved issue or indeterminate form that we will tackle. All right. If this was infinity minus a number, it would still be infinity. Right? If this was infinity plus a number, it would still be infinity. If either one of these is a real number, the infinity sort of swallows the whole thing up. But because I have infinity minus infinity, it can't be resolved easily. Yeah. So here's what we do. We go back to here and we use another technique. We need another technique. And it's actually not new. I'm just going to put it in air quotes that it's new. We've already done this before with polynomials, right? We had infinity minus infinity plus infinity minus infinity. All of these terms went to infinity. And we're like, well, how do we resolve that, right? And the way we did it was we divided everybody by the largest power. All right? So watch. Well, first thing I'm going to do is switch from negative to positive. Again, that's optional. If you want to do the whole calculation with the infinity being negative, you certainly can. I like to avoid any issues with, negatives and double negatives and things like that, so I'm just switching. So all of what used to be negative becomes positive, and what used to be positive becomes negative, and now I can use that definition that we just learned. And now I'm going to divide all of the terms by the largest positive power. So the new technique is to divide all the terms by the largest positive exponential. So that'll be e to the 4x. So it's going to be 7 over e to the 4x minus 6. Notice when you divide that one, I could write it. It's e to the 4x, e to the 4x. Those are going to cancel out. So it's just going to be 6. And then I'm going to get 3 e to the negative 5x over e to the 4x. And what this does is it kills one of these infinities. It's going to turn one of these into a number, and then I can resolve it. So I've got the limit as x goes to infinity now, because I switched the powers, of 7 over e to the 4x minus 6 all over 3 over e to the 9x. All right, and again, I'm not showing that math again. I already did it. It's negative, negative, negative 5, negative 4, which is negative 9, but I'm putting it down in the bottom. All right, so now what's going to happen is this is going to go to 0. Yeah? This is going to stay at negative 6. and this is going to go to 0. And so I'm going to have -6 over a very small positive number. My head's in the way. That's the reason why I switched it to positive infinity, because I want to know that this thing is getting very, very small, but it's a very small positive number. So it's going to go down. -6 divided by a very small positive number, the limit is -infinity. Which I'm really glad this happened, because when I look at these problems, I think, oh yeah, this is totally predictable, right? I know what's going to happen every single time. And I've been doing this for many years, and I'm still surprised. Sometimes it turns out exactly the way I predicted it would turn out, but sometimes it doesn't. And I end up with, a mess. So I'm glad we discovered this. And if you think about when I got intentionally stuck, because I led you down that road, infinity minus infinity, right? Your intuition fails you, because you can't think that an infinity and another infinity could subtract and cancel each other out and become 0. I mean, that could have happened. That could happen, but it didn't happen, right? An infinity minus another infinity ended up being -infinity. So let's keep this technique in mind. I might want to use it a little bit earlier, right? Because this is a quicker way of resolving it. You don't have to get stuck before you use the new technique. But sometimes this technique, you might use it and find out you didn't have to use it. You could have done it the more direct route. So it really is a mixed bag. You never know you're going to need the spare tire, until you get a flat, right? So it's good to kind of have it on hand in case you need it. It's your insurance there. Let's try another one and see what happens. All right, let's do the limit as x goes to infinity of 6e to the 7x plus 9e to the -5x over 4e to the -5x. All right. So let's just get right into it. I just showed you the technique. I have a feeling that we're going to need it. It's like I'm just having this feeling that we're going to get a flat. So let's go ahead and do the trick of dividing everybody by the largest exponential positive power. All right. That's because we're going to positive infinity. If you're going to negative infinity, then you would switch the powers, change it to positive infinity, and then use the same trick. All right, so this is the x goes to, I hate calling it a trick, but it kind of is. It's a technique. So this is going to be 6. Now again, I'm dividing by this, so I know that's just going to become 6. I'm just going to save the whiteboard here. The rest of them, I will show the math. So that's e to the -5x divided by e to the 7x. And then this one is 4e to the -5x divided by e to the 7x. All right, it's important that you divide everybody. You can't just pick and choose. When you divide all the terms by the same number, it's essentially like dividing by 1. Yeah, because you're doing the numerator and the denominator, and so it's like you divided everything by 1. Or multiplied everybody by 1, same thing. All right, so that's the limit as x goes to infinity of 6 plus 9 over e to the 12x, right? So it's negative 5 minus 7, which is negative 12. But negative 12 would go to the denominator and just be 12. You could also write this as 9e to the negative 12, all right? I'm just saving a little board space and putting it that way. And then down in the bottom, it's also 12, e to the 12x. No, that one's just a 1e to the 12x. All right, so again, this means the same thing as 4e to the negative 12x, if you prefer negative powers. I personally prefer positive powers. All right, but I mean, you do have all of the techniques for negative powers that we learned, so. All right, so the limit of 6 is just 6. The limit of this is 0. And the limit of this is also 0. This one's also 0. Right? It's 4 divided by a very big number. So this is 6 over 0. It's positive, positive 6. Now, there's no such thing as positive 0. But remember, this number is not actually 0. Right? If you put this into your calculator, you're going to get an error. Right? So this is actually 6 divided by a small positive number. And that will become positive infinity. Now watch this. This is a BOGO. Remember my BOGOs, my buy one, get ones? Watch this. You're going to love this. I'll take my pen and let's change negative infinity. Okay. Then we switch to positive infinity and change all the powers to negative. I take that back. The technique is to divide by the largest positive power. So I have to back up. There is no buy one, get one on this. I apologize. No buy one, get one. Wah, wah. I thought I could get 2 for the price of 1, and I did not get it. Because the technique, I have to remember very carefully what the technique was. It was to divide by the largest positive power. Well, when I do the switch, that's when I stopped and thought about it. I thought, oh, I could just knock out another one without wasting a lot of time. I would have just got the same answer. It's not true. When I switch from negative infinity to infinity, I have to also switch all my powers from positive to negative. And so now the largest power is not 7 anymore, it's 5. So I have to divide everybody by e to the 5x. So that'll be 6 e to the negative 7x over e to the 5x plus 9 over 4. Now again, I'm not showing that step mainly because I'm running out of room, but if I divide this by e to the 5x, I will just get 9. And if I divide this by e to the 5x, I will just get 4. So I'm just kind of conserving some space here. All right. Let's do some quick math here. I'm running out of board space, but that's going to be 12x in the bottom. Let's just go ahead and do that. I guess I could have just done that here. Yeah. When I divide this by 5, it subtracts, so it becomes -7 minus 5, which is -12, which I put down in the bottom and called it 12. All right. Now we got an asymptote. 6 divided by a very large number is 0, so this one goes to 0. This is a constant, 9, constant 4, and so the limit for this one is not infinity, but 9/4. I'm going to take off my hat and wipe off the sweat because I was really sweating it there for a minute. I tried to pull out, a second answer from one, and I almost fell into the trap. I caught it right about here. I went, wait a minute. What used to be the largest is no longer the same largest value. Sometimes you get 2 asymptotes. Sometimes you get 2. In this case, you only get 1, right? So you get the HA is y equals 9/4. But sometimes you don't get just 1. As long as one of these comes out a real number. But watch what happens, how you can get 2. For this one, I'm going to go back to the old f of x notation. I kind of gave it away, but we're getting close to the end, and I want to make sure I make this very clear. So when we do the limit as x goes to infinity, the largest positive power is just EX. There's no constant on the power. So I get, divide everybody by EX. So I get 7 over EX. Oh, I got to write limit. Seven over EX minus 10. 5 minus 6 over EX. And so again, x is going to infinity. This is going to 0. And so is this. So it's -10 over 5, which is -2. That's pretty easy. Yeah. Now that we have the technique down. Right, and also because the power is very simple, e to the x. Now, for the other direction, because these are all just e to the x powers, I'm not going to do the switcheroo. I'm not switching my x. And I'll tell you why. If I did switch them, then they would just become -x, right? And then I wouldn't have a largest positive power to divide by. Right? So if all of the powers are already positive and then you switch them all to negative, well, then you've lost the ability to use that trick. However, we do know a lot of these limits. From the very beginning of this course and this lecture, kind of combining everything we learned about how limits behave. And I know it takes a lot of writing, but this really kind of sums up everything. the limit of a function, all right? That function is a quotient. So I have the numerator and the denominator. Then I have a difference. So I break it up into two separate limits. I have a sum. I break those into two separate limits. I have constants. Those are just going to remain constants. I have the coefficients, the 10 and the 5. Those will come out in front of the limit. So the only limits I actually have to calculate are the ones that I learned or that we learned or I demonstrated at the very beginning of this lecture. And those limits both go to 0. Yeah. Very beginning, we drew the graph of the EX function, and X is going to negative infinity. So this is an example where keeping the X at negative infinity is to your benefit because you already know what that limit is. And again, you can use that for any of the limits that are exponentials in which you already know what it's going to be. Right? The only time I do that switch is if I'm like, I'm not sure if it's going up or if it's going down or if it's going, to 5 or to 0 or whatever it goes to. All right, so this clearly goes to 7 over 6 because these are going to cancel and I get a second asymptote. So this type of graph has 2 horizontal asymptotes. And another one like that. This one doesn't make, the graph is okay for this one. It's not that ugly, but because of the fractions and things, I'm going to show you one more with the graph included and sort of summarize everything and wrap it all up there. I'm already getting close to overtime. So let's graph a very related function. Now that you've seen the technique, you'll be able to see how nicely this works out. All right. So let's go ahead and graph this. The limit as x goes to infinity is going to be the limit, and divide everybody. See how quick you can do that when you get the technique down? It's especially easy when the exponents are just EX. This is going to go to 0. This is going to go to 0. And so that's going to go to 2. Positive 2. The negative infinity limit again, I'm going to leave it as negative infinity. Yeah. It's going to be 2 times 0. Right? Because I know that EX is 0. Yeah, I know that. I just carry that around in my mind. As long as X is going to negative infinity, it's 0. So I know that's going to be 0. That's going to stay negative 14. This one's going to be 0. I'm just copying my function down here. And then plus 2. And I get another horizontal asymptote at negative 7. And that's why I saved this one for the graphing example, because it's very easy to graph. It's kind of interesting, I think. And it will relate to some of the applications that we do in the future. This is the whole reason why I'm doing all of this, so that when we get to those applications, you can go, oh, that's like that one function that we saw with the 2 asymptotes. Really only occurs in this in this arena. All right, so we're going to go 1, 2, 3, 4, 5, 6, 7. And put an asymptote. All right, and then we're going to go, oh, shoot, that's the wrong one. It's -7. The other 7. 1, 2, 3, 4, 5, 6. -7. All right. And then 1, 2. All right, now I only need 2 points. All right, those are my asymptotes. My 2 asymptotes. Now I just need a couple points. Any points will do. Just plug in a couple numbers. Now, at the beginning of this lecture, I said 0 is a good one to memorize. Yeah. Remember, e to the 0 is 1. Keep that in mind. So that will become 1. So 2 times 1 is just 2. And this will become 1. 1 plus 2 is 3. So that'll be -12 over 3, which is -4. So right about here, I get a dot. All right, I just need one more dot. One more dot. It's probably not going to be pretty, but you could just put something on here that's a decimal. Everything else is going to be decimals. So I've got 1. 1 is a good number to pick if you don't know what to pick. 1 and 0 are good starts. So you're going to get 2e to the 1 minus 14 over e plus 2. E to the 1 plus 2. I got my calculator handy. Okay, so I got e. There's my e times 2. Minus 14. So I get -8.5. I don't really care about the decimals. And then I got e plus 2. So there's my e plus 2. Gives me 4.7. So I get 8.5 negative 8.5 divided by 4.7. So it's approximately -1.8. All right. So x was 1, and this is right about here. Why did I need that? Because I just wanted to see which direction the graph is going. If this point would have occurred over on this side, then I would have gone the other way. If this point would have occurred down here, then I would have gone this way. But you know they have to go in opposite directions because one of them is going to infinity. Yeah, that's the one that's 2. And the other one's going to negative infinity. That's the one that's -7. So I knew that they were going in opposite directions, but I had different possibilities for which way it goes. So that is your graph with 2 asymptotes. And this reminds me of a problem that I had when I was in this course many years ago. Not just a problem, but an entire exam that I took when I was in college back in the 1990s, called the Most Difficult Math Test. So I had a professor at Berkeley that his grades followed a very simple formula. Very simple. Very simple if you are a math major. And it fits right in. This is an application, we'll call this, app. Sorry, there's no money involved in this, but someday there might be. This type of formula could be used to predict other things besides your test score. And so my math professor would use this formula to predict the percentage score based on the hours of study. Now, of course, the professor doesn't really know how many hours you studied, but the professor would tell us, if you study for 5 hours, plug in 5, and that'll predict what you'll get on the upcoming test. So it was more of like a take-home kind of thing. The test wasn't take-home, but the predicting what you're going to get was like, before we had you guys have Canvas now, right? You have the what if scores, what if I do this? Well, this is kind of like an old 1990s version of the what if score. So T is the hours of study, and K is based on the difficulty. It's usually a decimal, all right? So let's do an example. We'll call this example 10. I took a test that had a difficulty level of 0.17. K is usually a decimal, and the value of the decimal sort of is like a range of how difficult it is. It's a moderately difficult test. If it's a very small decimal, it's less difficult. Speaking of difficulties, I've been talking so long, but I do not want to make a part 4. So just hang in there. All right, so what score do I get if I study for 6 hours? All right, based on this difficulty number. Well, let's see. 6 hours of study for the test. So we're going to plug in 6. It's a good idea to multiply the K and the T first. We've done this earlier in this course. So K is 0.17 and T is 6. I kind of want to use my old calculator for that one. It's just faster. 6 times 0.17 is 1.02. So I've got 3.8 e to the 1.02 minus 1 over 0.05 e to the 1.02. And this will tell me approximately what I should expect on the test. Now let me show you why I taught you a lot of those tricks. All right, you don't want to put all this in your calculator, although you can. Right, if you just want to get this over with, maybe you've got a fancier calculator than me. They make some pretty fancy ones. You can just type this whole thing in, press the enter button, and out will pop the answer. But if you want to do this the sort of old school way, which is also practicing the techniques we learned, divide everybody by the largest power, which is e to the 1.02. And you'll get 3.8 minus 1 over e to the 1.02 over 0.05. Yeah, just dividing everybody by that. You could even continue to divide. That would be 3.8 divided by 0.05 minus 1 over 0.05 e to the 1.02. Now break out your calculator. 3.8, I'm going old school here, divided by 0.05, which is 76. And then this is going to be a small number. I don't know. Let's see. So we got 1.02 e. It gives me a decimal. Then I multiply that by 0.05. That gives me another decimal. And then I divide 1 divided by that. On this old school calculator, there's a 1 over x button here. And it gives me 7.2118. And then I subtract that. And I get 68.7 or 69%. You don't have to type the percent sign. You just say 69. I typically round to a whole number. So 6 hours of studying for this test, and I barely got a C. Yeah. I'm going to have to wrap this up now, but there's a couple things I want you to do on your own. So this is what I call the DIY. If you plug in 0, I'm going to leave that for you to do. It's pretty easy. Just plug 0 in everywhere there's a power. This problem will get very easy very quickly. Remember, e to the 0 power becomes 1. So plug that in. This will tell you the score you would get if you didn't study at all. Right? And so sort of was the reason for this formula was to kind of say, well, you know, studying is important, but sometimes you can study for 10 hours and it's not going to improve your grade very much because oftentimes what you know is what you know. But in other cases, studying for 8 hours might actually help you, right? So that's why these formulas are used to sort of adjust and predict your investment, you know, of time, because time is an important investment that you put into this course. All right. And then finally, if you take the limit as t goes to infinity, and I promise you, you will get a number. This limit exists. All right. It's definitely larger than 69%. But it is smaller than 100%, all right? Go ahead and take this limit, and this would be the highest possible score that you could get if it was possible to study for infinity hours. And we all know that it's not possible to study for infinity hours. But if you could, that's how this example would work. It seems like this video has gone on for infinity hours already, but it was very important that I concluded the section on infinity. And I wanted to get it all done without having to do a part 4. So thanks for hanging in there with Dr. J. Until we meet someday in the real world, I'm Dr. Jordan. I'll see you on the internet.